last lecture, we talked about these unions, arbitrary unions that you can do with sets. So unions of n elements, and here could be 100 or 1,000, or intersections of the sets. You can also talk about infinite unions. So you have an infinite number of sets, and you take the union of all of those using this notation from I equals 1 to infinity. That means that this is a union of all those sets, and similar with the intersection with this notation here. And there are ways in which you can do unions and intersections of even larger groups of collection of sets, but we're not going to talk about those things in this class. Just infinite, this kind of infinite is enough. There are other kinds of infinite unions and intersections which are not for this class. So, all right, so let's practice that a little bit. So let's look at this example about unions and intersections. So let me go ahead and start with that example. So let's say this, consider the set, let's say A sub n, and this is going to be a set that's going to depend on the number n, and this is going to be the set n, comma, n plus 1, comma, n plus 2, and so on. So this is an infinite set itself. This is considered sets an for n in the natural numbers. So before we do anything with those sets, let me just I'll give you like some examples of them. So for example, so let's say we want to know what is A1, right? So the first set. So A1, in this case, the n is 1. So this set will start at 1, right? So this will be 1. 1 plus 1 is 2, 3, and so on. Okay. This is actually equal to the natural numbers, okay? Because natural numbers 1, 2, 3, and so on. Now let's look at A2. So what would be A2? Now in this case, the n, the index here will be 2. So that means I'm going to start this set an at 2, and you basically increase by 1. So this is going to be 2, 3, 4, and so on. So that's not the natural numbers anymore. Let me do one more. So for example, A3, 3, 4, 5, and so on. So there is an infinite number of them. So a set for every natural number. So we have an infinite number of sets here. So let's see, for example, let's try to answer some questions here for this type of sets. So the first question will be, what is, for example, the union from I equals 1, let's say, to 4 of A sub I. Okay, and let's make an interpretation of what that means. So what would be the interpretation? This will be A1, right? Union A4. So we use this notation just to save some writing here, just to save notation basically. Okay, let's look at the sets here. So what would be this whole union? Now remember that the union is the collection of all elements that is in either one of these sets. Okay, so A1. So A1 is here, 1, 2, 3, 4, and so on. A2 is 2, 3, 4, and so on. A3, it'll be 3, 4, 5, and so on. And this A4 will start at 4. So 4, 5, 6, and so on. So what do you think this union is going to give us? So that will give us the natural numbers. Very good. All right, so let's look at another question. So let's say, what is, let's say, the intersection instead of the union? Let's look at the intersection from 1 to 4 of, let's say, A sub I. Right. So this is not union. This is now intersection. So this is will start as A1 and then intersection A2 and then intersection A3 and then intersection A4. Okay. Now, always when you're doing this type of things, so just pay attention on how the sets are defined so you can get the answer for this one. Okay, remember intersection is the collection of elements that is in all of them. So an element is in the intersection. If it is in A1, it has to be in A2, A3, and A4. It has to be in 4 of them. Now, in these examples, we are just doing a computation. We are not doing a proof. Now, doing a proof will be different because if we are asking what is that and it doesn't say a proof, usually what it means is that you just find it without giving any argument. But if it says something, prove that this is natural numbers, then you will have to do a proof for that. But in this case, we are just trying to see what those sets are. Okay. The last thing I'm going to do in that section, so I'm going to move into section 1.3. So 1.3. This is going to be the section that is called the axiom of completeness. The axiom of completeness, this is the part where we can actually define what a real number is. So the question we actually want to answer here a little bit is, what is exactly a real number? Now, if you remember what we did for the last class, I gave a geometric idea what a real number is. That's not the real definition, the mathematical definition of what a real number is. Remember, real number is represented by the points of the real line. That is not a really mathematical definition of it. What I'm going to give you right now is a little bit better, but not exactly what we need to, what the real number is. So I'm going to give you this. So R, or the real numbers, is an extension of the rational numbers. So it means that Q is inside R, in which there are no holes or gaps. Now, this is a little bit better than the one I gave you last time, but it's still not precise. So this first part is actually good. R, the real numbers, is an extension of Q. So that means R contains Q, or Q is containing R. It's an extension of Q that has this property which has no holes or gaps. Now, having holes or gaps is not a mathematical definition. So what we're going to try to do the rest of this section is try to formalize this idea. What does that mean to have a hole or a gap? So we want to formalize this idea. So let me write that down. So we want to formalize this idea. What idea? The idea of what it means to have a hole or a gap. So let's start with actual mathematical definitions. So let's write down a definition here. So definition. This is going to be a definition of bounded above. So bounded above. Now, all of these definitions and theorems we're going to prove, this is all leading to the definition of what the real numbers are. So let me say what a bounded above is. So a set X included in the real numbers is bounded is bounded above, and this is where we are defining. So we are defining what bounded above means. Bounded above, if there is a real number m such that for all lowercase x in capital X, we have that x is less than or equal to the real number m. I'm going to give you an exact idea of what bounded above is with a picture, but this is the actual definition of bounded above. So what you can keep in your mind, bounded above is if you have a set and there is a number m that is bigger than any element in that set, that means that we call the set X bounded. Okay, so let me give you a little bit of a picture here using the real line. So let's say, for example, your set X is some sort of maybe some interval here, not necessarily an interval. This is going to be your set X, and that set X is going to be bounded above if I can find some real number m so that every element that I take in the set X is going to be less than or equal to that number m. Okay, so if that happens, the set X is called bounded above, and this real number m is called an upper bound of X. So let me write that down. M is called an upper bound of X. I'll give you some examples, okay? Now, if I really want to be extremely precise or use the notation for mathematics, if I want to define what bounded above is, I will write something like this. There exists a real number m. This is the notation here. There exists a real number m. So for every x in the set X, then x is less than or equal to m. So let me move this here. So this will be the really formal definition of that using just math symbols. So all of that is written here in English. All of this part in English right here, this one can be translated into symbols using just that. Okay, so let me give you an example here of some sets that are bounded above, some others that are not, and so on. So let's look at some examples. So example here. So let's look at this example. Let's take the set X equal to 0, 1. This is as an interval. So the interval 0, 1. So we just look at the real line, and this is 0 and this is 1. Then the set X will be just all of these numbers between 0 and 1 without including the 0 and the 1. So that will be the set X. So let's look at some upper bounds. So the number m equals 2 is an upper bound. Okay, 3, right? 3 is also an upper bound. So if you have an upper bound, most of the time you have many. So a set is bounded usually not by a single number, but usually by many. So let me make that clear here. Let me say the set X equals to the interval 0, 1 has infinitely many upper bounds. So upper bound is basically just a number that is bigger than or equal to the set, to all the elements in that set. Okay, let's see another example here. So this example, let's say the set X, and I'm gonna give this in a descriptive way. So as this set of all the elements of the form 1 over n, so that n is a natural number. So that is a set in the real numbers. So the elements here are this type is 1 over n, and the n has to be a natural number. So basically, if we draw this on the real line, so we have 0 here, and so you will have, let me use a color here for the elements. So that's 0, and then you will have a 1 here, and then the other element will be somewhere over here as 1/2, and then you will have 1/3 somewhere over here, and then you will have another one here, 1/4, and so on and so on and so on. Okay. 1 works, exactly. Very good. Number m equals 1 is an upper bound. Now, an upper bound could be in the set. In this case, m equals 1 is an upper bound because every element in this set is less than or equal to 1. Okay. Now, this is not a proof. So if they ask you prove that is an upper bound, then you will have to do a proof. Here, we're just looking at the answer here. Okay. And of course, this is going to have tons of upper bounds. So for example, m equals to 1.1 will also be an upper bound, and basically any number that comes after 1 will be an upper bound for the set X. So let's look at the next example. Let's say number 3. Let's take this set X, which is the natural numbers. And remember, here the natural numbers are just 1, 2, 3, and so on, right? In this case, this set doesn't have an upper bound. Okay. So X, in this case, X has no upper bounds. So it's possible that you don't have an upper bound. So some sets have it, some sets don't. Okay. Okay, let me ask you a question here. Is bounded above the same thing as an upper bound? Bounded above is a property for sets, right? And an upper bound is a number, right? Exactly, very good. All right, so let's do something similar now for when you have the definition. So this definition that is called bounded below. So bounded below. So it's exactly the same thing as before, but now instead of having a number that is bigger than or equal to all the elements in the set, then you have a number that is less than or equal to all the elements in the set. So let me give you the precise definition here. So is set X that is a subset of the real numbers is bounded below, and that's the thing that we are defining, bounded below, if there is a real number, let's call it a lowercase m, such that this happen for all element X in the set X, if X is in capital X, then M is less than or equal to the number X. So basically what we are saying is something is bounded below if you can find a real number M that is less than or equal than all the elements in the set X. So if we were to draw a picture in the same way we did with the other one, so let's say you have your set X here. So that would be your set X. And the so bounded below means that you can find some real number M somewhere on the left of that set. So this number M is less than or equal to all the elements in that set. And if we want to be really, really precise, bounded above means that there exists a lowercase m in the real numbers. So for every element, for all x, in the set X, we have that m is less than or equal to the element x. Okay, so this is the definition using only mathematical symbols, and that's going to be a translation of what this one says right here. Okay, I'm going to give you some examples as well. Okay, the real number here. Okay, thank you. Okay, so in this case, when that happens, we're gonna call this m a lower bound. So in this case, we say that m, we say that lowercase m is a lower bound of x. Okay. So this is analogous to the we have before. We have upper bounds and bounded above, and now we have lower bounds and bounded below. Okay. All right. Let's see some examples. Now let's look at that example we saw in the other part, and the example was, let's take the set X to be the natural numbers. So, which is, remember, 1, 2, 3, and so on. M equals to 0 is a lower bound. Well, that's because 0 is less than or equal to that all the numbers in the natural. So the natural numbers, so it's going to be 1 here, 2 here, 3 here, and so on. So that would be the set of all the natural numbers that go on forever here on the right. But the number 0 here, so that would be a lower bound for that set. And there are many, right? Let's take this set, the set X, which is equal to the elements that have this form 1 minus 1 over n. So let me move to this page. Let's see if that works. No, right, okay, that works. So let me write down again the set 1 minus 1 over n, and then in this case n is in the natural numbers. Okay, in this case, can somebody please give me the first 3 elements of the set X? So with this set, so we have the elements, and so are 0 here, and then it goes, then let me put a 1 here. So then we'll have a 1/2, and then we have 2/3 is somewhere over here. I'm gonna erase the number 1 here because I don't want to give you the idea the number 1 is in that set. So it's 2/3, and then after that it's 3/4 somewhere over here. Okay, this is not a scale. Okay, and then the number 1 would be somewhere over here. Now the reason I want to point this out is because the number 1 is not actually here. What's going to happen here for this set is, if you can look at what happens here, is all these numbers, so start 0, 1/2, 2/3, 3/4, the more that you increase the n here, the closer these numbers are going to be to 1, but it will never reach 1. So m equals 0 is a lower bound. Okay. Does the set X have an upper bound? M equals to 1 is an upper bound. So that would be an upper bound. Okay, questions about that example? Or any questions about lower bound and upper bound? So whenever you have 1 in the real numbers, you're always going to have like infinitely many.
Okay.
For the real numbers. Yeah. Mm-hmm. Correct. Now, if you're still wondering why are we doing this, all of this is preparation to give a proper definition for the real numbers. So we had to do all this preparation just for that. Okay. So let's move into this another definition. So this definition is a definition of least upper bound. So let me explain what that is. So a real number S is the least upper bound of a set X that is already a subset of the real numbers if the following happens. So the following happens. Two things have to happen here. Number 1, so we are saying that S is going to be the least upper bound of a set X. Two things needs to happen. The first thing needs to happen is that S is an upper bound of X. So that means that the element S has to be bigger than or equal to all the elements in X. So that's the first part. And the second part is that if B is an upper bound so if B is an upper bound of X, then S has to be less than or equal to B. Okay, I will explain what that means. Okay, least upper bound. The name here, least, means it's kind of the minimal, the lowest upper bound. So the lowest upper bound is a number, a real number, that is bigger than or equal to all the elements of X, but has the extra property that if you have another upper bound, then S, the least upper bound, has to be smaller than all other upper bounds. So again, take all the upper bounds and choose the smaller one, if you will. That will be your least upper bound. So that would be that one. So this least upper bound is also called, it has another name, which is the most common one, the least upper bound So the least upper bound is also called a supremum, which I'm gonna be calling it from now on like that, the supremum of the set. And we're gonna write down this notation. So we write that S is equal to the supremum, which is, we're gonna denote like this, SUP, the supremum of the set X. Okay. So whenever you see something like this, as UP means the supremum, if there is one, with that set. So that supremum, again, let's go back to the definition. What is a supremum, or least upper bound of a set? It has to be, first of all, it has to be an upper bound. That's the first thing that needs to happen. And the second property, which is this one, basically means that's the smallest upper bound that you can find for that set. Okay. So let's look at the set X. So let's say that the set X is the interval from -1 to 2. So this is going to be an interval. Okay. And let me draw the interval, so to give you more or less an idea. So let's say -1 is here, and then let's say 2 is somewhere over here. So we are looking at that interval so it's an open interval from -1 to 2, and is all this inside that interval, so all the numbers there. I'm not gonna do a proof. In this case, we are just gonna look at this and see if we can find the least upper bound, or the supremum. So in this case, what would be the supremum of the least upper bound of the set X? Remember, two things need to happen. One, it has to be an upper bound, and second, it has to be the smallest of all the upper bounds that you can find. Is the supremum of the least upper bound. So you hear for the set X, everything that is to the right of 2, or is 2, is an upper bound, but 2 is the smallest one here. Okay. Now I'm going to make a note here. The note here is, notice that 2 is not an element of the set. Okay. So what that basically means is this. I'm going to write down this better. Notice. What that means is that the least upper bound does not have to be an element of the set. So the least upper bound here is 2, but it's not an element of the set X. Let's look at some other example. Example number 2. So let's look at this set X, which is, let's say, the interval from 0 to 1. And that's this is also an interval. So in this case, again, the picture, let me scroll down here a little bit. So the picture will be something here. This is 0, and 1 will be here. And so now the set will be open at 0 and close at 1. So it will be all the elements here. So if we just have to say, just by looking at it, what will be the least upper bound or the supremum of this set? In this case, the least upper bound is in the set, right? So in this case, let me write that down. In this case, 1 is an element of the set. What I want to point out here is this. Whenever you have a supremum or the least upper bound of a set, that supremum might or might not be an element of the set, okay? Why am I saying this? Because sometimes in a proof, when you are proving something with the supremum, you can never assume that the supremum is an element of the set unless you can actually prove it, or you are told in the hypothesis that it is an element of the set, okay? Okay, let's do the third example here. Let's take this set, the set X, which is the set of the rational numbers. Does this set have a supremum? Okay, any reason why the set does not have a supremum? So here you don't have a supremum. The reason for that is does not exist. Let's just put that down. Does not exist because Q does not even have an upper bound. So if you don't have an upper bound, you have no hope of having a supremum. Supremum is a particular upper bound. So if you don't have any, you cannot have a supremum. Okay. All right. Let me make a couple of remarks before we go into the next things here. So let me do a couple of remarks here. And whenever you are doing proofs or doing something with upper bounds, I always want you to remember these remarks. Okay. So the first one is this one, that the supremum of the least upper bound of a set is a real number when exists. So sometimes it doesn't exist. So the supremum might or might not exist. I'm gonna put that as the second one. Supremum of X might or might not exist. Okay. So sometimes it's always a real number when it exists, but it might not exist. So when it exists, it is actually a real number. And the third one, and probably the one that I've seen most people making mistakes, is this one. The supremum might or might not be an element of the set X. So the supremum does not have to be an element of X. So let me go into an example here. Just one more thing, just to emphasize the points here. Let's look at the set X, something that we saw earlier. This is the set 1 minus 1 over n. N here is a natural number. Okay, so let's draw a picture again. I know we did it already. So that's 0. And then somewhere over here is 1/2. And then somewhere over here is 2/3. And then a little bit later is 3/4, and so on and so on and so on, right? Now I drew a picture of this, emphasizing that we have 1 here. And as you go up here in this set, these numbers are getting closer and closer to 1, but 1 is not an element of this set. Now, this is not a proof, so we're not doing proofs yet, but let's try to just use the picture just to get an idea what the supremum or the least upper bound is, or if there is any. Now, does this set have a supremum? Yes, it's true. This is a little bit more difficult to see, and we will have to prove this later, but 1 is a supremum. Now, if you look at this, 1 is, of course, what properties do we need to have a supremum? 2 things. What is the first thing a supremum should have? So it has to be an upper bound. That's property number 1. What is the second property that a supremum should have? Why is it the smallest? If we cannot prove this now, but we will prove it later. If you keep going up here, these elements are going to get closer and closer to the number 1, but it will never be 1. So that's going to make 1 an upper bound is going to be the smallest of all of them. So here the supremum of that will be 1. Okay, it's like taking the limit. So in this case, when you take the limit of this sequence, 1 minus 1 over n, take the limit to infinity, then that limit will actually be, in this particular case, that limit will be the upper bound. Very good, yeah. Not always, but in this case it is. So the limit will be the supremum. Yeah. Okay, so we'll finish the class with a proof. And this proof is not very long, but let's make the statement and then let's do the proof of that. Okay. So the proof is this is going to be the first thing we're going to prove. So this is a theorem. So the theorem is this. Let A be a subset of the real numbers. If A has a least upper bound or what we are calling the supremum, in that case, if it has 1, then it has to be unique. Then it is unique. Now, this is important because remember we saw earlier in the lecture that upper bounds do not have to be unique. Upper bounds are not unique, but if you have a least upper bound, it is unique. So if you have at least 1, that's it. That's the only one that exists. Now, if you're taking abstract algebra with me or maybe some other proof class, there's a standard way to check that something is unique. So when I want to check that something is unique, in this case would be the least upper bound, I'm going to assume that there are two of them, and then I prove that they have to be the same. That will prove that there is only 1, because every time you assume that there is 2, at least 2 of them, then they have to be equal. So there is only 1 that has that property. Okay. So this least upper bound that is here, I'm gonna call it like this, just to not write down LUP that all the time. So let me write that down. So to prove that least upper bound is unique, we assume we have, so we have 2 least upper bounds. Let's call them S1 and S2 and prove that they actually have to be the same thing. So they have to be the same upper bound. Okay. I haven't proved anything. I'm just saying that's the plan. Okay. Let's unravel what all of this means. Now, first thing I'm going to do is let's write down exactly what S1 being an upper bound mean. So let's write that down. So if S1 is a least upper bound, that means exactly 2 things. Let me call it A and B. So if S1 is a least upper bound, what is the first thing that S1 has to be? So S1 is an upper bound. So which is what you just said, that S1 is bigger than or equal to all the elements in that set. Let me write down that a little bit better. So that is that S1 is bigger than or equal to X for all X in the set A. Okay, that's the first thing that has to happen. All right, let me ask you this question then. What is the second thing that S1 has to be for it to be a least upper bound? So let's write that down. So if B is another upper bound, then S1 has to be less than or equal to that specific B upper bound. Okay. Now, so that is this couple of things is just the definition, right? I'm just writing down straight definition of what it means to be least upper bound. I'm going to do exactly the same thing for S2 because we are also assuming that S2 is also an upper bound. So I'm going to write down that here. So if S2 is an upper bound, then two things had to happen. Let me call that C and D. Okay, so that in this case is S2. So, okay, what is this property here, S2? If it's an, least upper bound, right? So if this is a least upper bound, what is the two things that need to happen? Number one, S2 is an upper bound that is that S2 is bigger than or equal to X for all X in the set A. C is another upper bound of A. And then what has to happen in this case? S2 that's not equal to C. All right, so we are almost done here. Okay, we're almost done. So we just wrote down the fact that S2 is a least upper bound, which is that part there. And then now we have that S1 is a least upper bound. Now, let's combine things here. Now, so here, let me write this here, and you tell me this is true. S1 is an upper bound. Right, so it's just this part, right? This part A that is here, right? S1 is an upper bound. Let's say Y. This is by A. Okay. Now, let's use now that S2 is a least upper bound. And let me look here at part D. Part D says, if you have an other upper bound of A, then S2 has to be less than or equal to that upper bound. So here in part D, I can use S1 as my C. Okay. All right, let me go back here to the previous page. Now I'm gonna say this. S2 is an upper bound, and that is because of C. So I'm gonna say that here. S2 is an upper bound. It's an upper bound. And before we go on, I'm gonna give this first inequality, I'm gonna call it number one. So S2 is an upper bound. This is, but why is this true?
From condition C.
Right, by C. Now, I'm gonna take S2 as my upper bound. And let me go back to the previous page, and I'm gonna show you the definition for S1. So S1 is a least upper bound. And let's look here at part B. Part B says, if I have another upper bound, then S1 has to be less than or equal to whatever upper bound you have. So let me go back here now. So because S2 is an upper bound by C, since S1 is a least upper bound, then what can I write down here? This is the least upper bound, S1, and S2 is an upper bound. So what inequality should be true here? And I'm gonna call this one 2. All right, what can we conclude from 1 and 2? S2 is less than or equal to S1, and S1 is less than or equal to S2. The only way that that could happen is if S1 is exactly the same as S2. So let's make the conclusion here then by 1 and 2, S1 has to be equal to S2. So that's the plan from the beginning. The plan of the beginning was I assume that there are 2 least upper bounds, and then by doing this argument, this is unique. So this is what we wanted. And when you finish a proof, you put a square there to indicate that we are done. Okay. All right. That will be the end of the proof. That's all I have to say for today then. Unless there are questions, I'll stop here for now.